Our previous lesson, what we learned about was the Pythagorean theorem. And the Pythagorean theorem can only be used on right triangles. It can also only be used when you only have side lengths. Only right triangles and only dealing with side lengths. So, of course, there are times when we're given a triangle, a right triangle, where we aren't given all of the side lengths, and sometimes we're given angles. And we can still solve for any part of that right triangle that we want to using what we know as trigonometry. I'm expecting that most of you have seen this before in some capacity. If you have not, definitely let me know and we can spend more time in class discussing it. So first I'm going to just draw a right triangle. Then I'm going to label one of the angles. I'm going to label it as theta. Theta is a Greek variable, and it's a Greek variable that's used all the time with trigonometry. You will see it all the time. So this is like replacement of x, really, in this idea. So with trigonometric ratios, what's really important is the relationship of the side lengths to this angle in particular. Realize if I focus on a different angle, your relationships would be different. So the relationships that we have are, first of all, hypotenuse. Hypotenuse is the easiest one to spot. It's always opposite of the 90-degree angle. So it opens up from the 90-degree angle. This is your hypotenuse. Okay. The other two ones are opposite and adjacent. Opposite means across, like the hypotenuse is opposite of the 90-degree angle. You can think of it as a spotlight, right? Think about this as the spotlight that's up on the balcony of a theater, and you're like moving it to something to focus on, and this is your light source, and this is what it's focusing on. It's opening up to this side length right here, and this is your opposite side length. The last one that's left is the side length that is next to it, which we call the adjacent side length. I always label this one last in relation to all the other ones because sometimes adjacent can get a little bit tricky to spot. A lot of students try and call the hypotenuse the adjacent side length, and don't do that. Don't be that student. Your hypotenuse has to be the longest side length, and your adjacent is the other length that is connected to make that angle. Now, the relationship of these angles to these side lengths will always be consistent. You have something called sine of theta. Now, theta is inside of sine. Think of sine as this computer that takes an input, and this input is theta. So theta goes into sine, and sine gives back a relationship, and that relationship is opposite over hypotenuse. So the sine of this angle is equal to the opposite side length divided by the hypotenuse. We have something called cosine of theta. Cosine of theta has the relationship of the adjacent side length over the hypotenuse. And then we have tangent of theta. And tangent of theta is equal to the opposite side length divided by the adjacent side length. And we have a way to remember this, and it's by using the three letters in each of these situations that stand out to us. So S, O, and H, C, A, and H, and T, O, and A. We call it SOHCAHTOA. So you'll hear that a lot of SOHCAHTOA trigonometry. And what it's referencing is right triangle trigonometry. Again, this can only be used on right triangles, and it's because we're talking about a hypotenuse here. And you cannot have a hypotenuse if you're not talking about a right triangle. All right, let's go ahead and practice these. I would like for you to take out your calculator. So you click on this trig button here to the side, and you'll get this these options popping up. We want to click on sine, and then you plug in 30 and enter. If you do not get 0.5, you need to change the mode of your calculator. If you go to menu, oh, no, I lied. You go to doc and then settings, document settings, This guy right here needs to be degree. If it says radian, you need to change it to degree, and that would be why. So if you got something else besides 0.5 TI-84s, go ahead and Google it on your own, how to change the mode of a calculator of TI-84, and it will give it to you. So we get that sine of 30 is 0.5. We'll go ahead and do sine of 45. We'll do 3 sig figs. Sine of 60. Which is 0.866, and then sine of 90, if you type it in, you get 1. I would like for you to go ahead and do the rest of these on your own, typing them into your calculator. You'll notice that cosine and tangent are just your two options to the right of sine. Go ahead and fill those in. Okay, so these are the values that you should be getting for the rest of these. If you're having any issues with typing in these trig functions into your calculator, definitely let me know. It's something we can work through in class together. But this is pretty straightforward. Now, the question here is a little bit less straightforward, but hopefully you notice some things that are going on with sine and cosine. Notice that sine of 30 and cosine of 60 are the same. Notice that sine and cosine of 45 are the same, and then sine and cosine of 30 and 60 are the same. This will always be true of a relationship as long as that the values will be the same between sine and cosine as long as the angles add up to 90 degrees. So notice that 60 plus 30 is 90, 45 plus 45 is 90, 30 plus 60 is 90. So if I did the same with sine of 50 and cosine of 40, because those 50 plus 40 is 90, if I take those values, those will be the same. It's just a little relationship. You don't have to have it memorized. It's just something that you might have noticed throughout here. Something else you might have noticed is that these values are all under 1 or at 1. And cosine of 0 would be 1 because 0 plus 90 is 90. And the reason being is you have to look at how we make these values. So, and this is what it asks you for E, explain why any angle theta, where sine of theta is less than or equal to 1 and cosine of theta is less than or equal to 1. Why is it doing that? So look at what's going on. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And you have to think about, what do we know about the hypotenuse? What are some things that we know about the hypotenuse? We know that the hypotenuse will always be the longest side. Always, always, always. That will always be the relationship, which means that no matter what's going on with opposite and adjacent side lengths, if you put it in a fraction where the hypotenuse is in the denominator, that means that you will always have a denominator that's larger than a numerator, right? So if you had a 3 up top, then it would have to be 4, 5, 6, 7, 8, 9, 10, or any decimals in between. So that means it'll always be less than 1. So you can say something along the lines of sine and cosine will have a denominator of hypotenuse, which will always be larger than the numerator. This is different from tangent because tangent is opposite over adjacent, and there are no rules for opposite and adjacent. One opposite could be larger than adjacent, and adjacent could be much smaller. There are no rules about the relationships of those side lengths. And so as a result, the fraction relationship that happens there doesn't necessitate that it's less than 1. So that's how it's different from sine and cosine. Okay, so why do we learn this? We learn it for these reasons. We learn it for example 5, which is solving for side lengths. And we learn it for example 6, which is solving for angles. Again, I will say this to you a million times. Remember, this is only for right triangles. If you look later in our notes, we're going to be talking about non-right triangles. But for right now, we're only talking about right triangles. And that means that SOHCAHTOA can only be applied to right triangles. So this is solving for missing side lengths in right triangles and solving for missing angles in right triangles. Now, this is different from the Pythagorean theorem, solving for side lengths, because we don't have 2 out of the 3 side lengths. We have 1, and we're given an angle. That's how we know that we want to use SOHCAHTOA, is if we're given a side length or some side lengths, typically only 1, and an angle. So then we can use that angle to solve for the missing pieces. So we need to solve for y and for x, and we're given the hypotenuse. Think about your relationships here first. Think about what is hypotenuse. I always label my hypotenuse first. And then your opposite, I label next. Opposite, remember, is that spotlight across from 20. So this is your opposite. And then x is your adjacent. So if I wanted to solve for y, I would say, well, I can only have one unknown, and my unknown is this guy right here, which means I need to use my 2 knowns in order to build that up. So the relationship here is we have 20, which is the angle. We want to find opposite, and we have hypotenuse. And so you think to yourself, where on SOHCAHTOA do I see O and H together? And that's going to be right here. When you see O and H together, because we want to solve for the opposite and we have the hypotenuse, that means that we need to use sine. So I would do sine of 20, not sine times 20. 20 is inside of sine, equals y over 4. And we need to get y alone in order to solve this. If you know what to do, which is multiply both sides by 4, awesome. If you really struggle with problems that look like this, that is fine. I've noticed that it really helps a lot of students to take this guy and put it over 1. Because I think a lot more students feel comfortable doing cross multiplication. So if that's something that you're like, oh, now I know what to do, then do that every single time. So here we would cross multiply. Y times 1 is y equals, and then 4 times sine of 20. So then once you get y by itself, you can go over to your calculator, and we're going to do 4 times sine, or you can just do 4 sine, and then of 20. And you get that y is 1.37. We'll do 3 significant figures. Oh, and it says 2 decimal places. 1.37.